basically be 0 because B is super big. 1 over a million is 0, so you basically get 1. And 1 over 1 is 1. So when the mass of the sun is super big compared to the Earth, you just get this, which is indeed the same curvature circle you get. So here I prove that taking the sun's frame as an inertial frame is a good approximation when the mass of the sun is really bigger than the mass of the Earth. If you don't want to do approximation, you can go to the center of mass frame, and then you'll get this. Okay? So the rest of this lecture should be rather easy because we're dealing with complicated things, and we don't know how to deal with complicated things, so we just talk a little bit about it. So it's going to be easy. When I am standing on the ground or moving on the ground, we said there must be some forces other than gravity between the ground particle and my feet particle. My feet particle will get some force from the ground particle. There's going to be some F1 from this guy, some F2 from that guy, blah, 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 a bunch of forces. We don't really know the nature of these forces. These are not gravity. I don't know what that formula is. It's something other than gravity. So we don't really know how to compute just single one of them, and not to mention adding them up. Because if you want to analyze me as a system, you want external force. These forces from the ground are external forces because ground is not a part of my system. So what I'm going to do, I'm going to give up. I don't know how to compute this force, but I know if I add them together, I'm adding vectors. And if I add them together, this is going to be still a vector, and it can be in, I don't know which direction. I may be moving like this. So the force from the ground can have some direction. What we're going to do is call the component of this force that is normal to the surface normal force. And the component tangent to the surface is called friction. Normal force is always normal to the surface because we define it this way. The surface can give you a force in we don't know what direction, but we just call the normal component normal force and the tangent component friction. So friction is always tangent to the surface and normal force is always normal to the surface because we define it that way. Okay? So about the direction of normal force, it's always going to go out of the surface because the force is not sticky. I know the force between these two is like this kinetic spring. They can only push, they cannot pull. So the normal force from the ground can only go out of the surface. It cannot pull me into the surface. But I don't know exactly how big this normal force be because it is complicated. So in gravity, we give you the formula of gravity. So you can use gravity to solve. So you can use the formula of gravity, Gmm over r squared, to get the force, and then solve for acceleration. If you know how to compute the force. Here, we don't know how to compute this force based on the distance between particles and stuff. So the way we are going to test you is to give you acceleration and ask you to solve for force. You have done your homework for Newton's second law, The first one is I give you three forces, you add them together and solve for acceleration. And then I think part D or part C, I think in part D, I give you acceleration and I choose to solve for force. This is exactly what we're going to do for normal force and friction. Okay? Let's give you an example. Let's say right now, I'm standing still. This is not standing still. I'm dancing, so there is some force in the other direction. But if I'm standing still, and I choose my entire body as my system, then the acceleration of the center of mass of the system when I'm standing still will be how big? What will be the acceleration of the center of mass of me if I'm not moving? 0. Good. So this is what I mean by giving you acceleration. And now because we're dealing with like microscopic objects, so we're going to use external force equals center of mass acceleration. We don't know how to compute this normal force. So we are going to give you acceleration and use F equals ma to derive the normal force. Now, according to that formula, I need to find out the external force acting on me. There are gravity pulling every part of my body, and the sum of them will just be my total mass times gravitational acceleration. Because every single particle has small m times g, and after I add them together, I get my total mass times g. So it's just like this one. The total gravity on this system is the total mass times g going down. Okay? Now, the reason I'm not falling down is because there are some interaction between the particle of my feet and the ground. I don't know what that interaction will be, but I know I'm going to call the normal component normal force. And because acceleration of the center of mass is 0, the x component of my center of mass acceleration and y component of my center of mass acceleration should both be 0. So, if I look at friction, there's nothing to cancel it. Friction is the one in the x direction. If I set my coordinate like this, x is the horizontal one, y is the vertical one. So because I'm not accelerating in a horizontal direction, the sum of external force in the horizontal direction should be 0. This means that I cannot get any friction from the floor, because if I have, there's nothing to cancel it, and I will be accelerating horizontally. So, given the acceleration, I know how to solve the friction, because the horizontal acceleration is 0. This is what I mean by giving you acceleration and so for force. Okay? Now, let's look at normal force and gravity. They are in the y direction, so I need to look at the y component of acceleration. Let's take up as positive, so let's do it slowly. That formula in vector form is normal force as a vector plus gravity as a vector, which is the sum of external force equals the total mass and center of mass acceleration as a vector. Now, because I am not accelerating, so this is 0, and we get this. When you are actually going to use vector equation, you just decompose it. Now, the vector normal force is going up in the y direction. So if I write out this vector, it's going to be the magnitude times direction, which is m times the j direction. Okay? How about gravity? If I want to write out gravity, what will that be? What will gravity be? If normal force is n positive j, how about gravity? Say that again?
Negative j?
Yeah, it will be mg and negative j. Good job, Pablo, because it's going down, it's going in negative y direction. So if I write it out as factored form, it's going to be in the j direction, but negative. And the magnitude is mg. And this is 0. So because they both have j, I can take it out and just say n minus mg is 0. If this factor is 0, then the component adding out should be 0, so n minus mg is 0. Okay? So at the end, I solved that in this case, normal force will equal to the gravity, so that they cancel, and my center of mass has no acceleration. This is what I mean by giving you acceleration to solve for the force. We cannot use just the interaction from the particle to solve for the force because we don't know how to do that. So the way we question you is to give you acceleration and get a force. Okay? So the only reason that normal force will happen to be the same as gravity is because I am not accelerating. This is not true in general if I am accelerating. Let me give you an example. Let's say I am standing in the elevator. I brought a scale for some purpose I'm going to mention later. And I am standing on the scale. And I am standing still, not moving. But if this elevator is accelerating upward and I am standing still in the elevator, what is the acceleration of my center of mass? I'm standing in the elevator, going up with the elevator. So if the elevator has A going up, will my center of mass acceleration be 0? What will it be?
Is it the same as the elevator?
Exactly, yeah. It will be the same as the elevator. So my ACM will just be the acceleration of the elevator going up, taking up as positive y. Because you are moving with the elevator. The position of your center of mass may be different, but when you look at velocity and acceleration, they will be the same. They are both moving up or accelerating upward. You can be moving in either way. The velocity and acceleration can be in opposite direction. The elevator may be moving down, but acceleration is going up. But if I want to look at the normal force, force can only affect acceleration, so I only care about acceleration. Okay? Acceleration can be going up,